We're going to look at the questions on page number 9, the solubility questions. And this is how I think I'm going to do it. I'm actually going to try to give you a big screen so you can see all the different things. So I'll read the question, but you can have a copy of this there as you go through, or you can look back at your questions after. If you look at the partial key, you will see answers to a lot of these questions there, or some notes for that, which I think will help you out with this too. Okay, but we're trying to get a qualitative understanding about solutions and about solubility. All right, so I think I'm going to start out going to a demo here, and I think I'm going to flip away from this screen share and just so you can see this a little bit better. All right, so try to make this work pretty good. And the first thing here is I have a conductivity tester. All right, so this is hooked up and it's got some wires. And what happens is when I connect the current, the wires together, the light goes on. Okay, there's an electron flow. Now, if I put distilled water in each of these things, distilled water does not conduct electricity. It's kind of interesting. Tap water probably has enough ions to show this lighting up. But the distilled water doesn't. Neither does the distilled water here. So next thing I'm going to do is take a spoonful of sugar, because I think that makes the medicine go down. I'm going to take a spoonful of salt, which I'm going to grab over here. Sodium chloride, looking at right here. Looks like, oh, you can see here. Oh, I got to move this way back here. Get this to where you can see it. And I just put a spoonful of sugar in there, and there's some salt. Okay, I think we're pretty good in being able to see that. And next, I'm going to add my salt right here. All right, and then I'm going to stir these things up. And I want to stir them enough. Probably could stir them and dissolve everything in there. Both sodium chloride and sugar have a high solubility. But I want to get enough in here and not take forever to do this. So certainly a reasonable amount has had a time to dissolve. And I'm going to put my conductivity tester in the sugar solution. Let's see what happens. And it dissolves, but it doesn't break into ions, where the sodium chloride does. So sodium chloride breaks into Na plus and Cl minus, which are charged particles, and conducts electricity. The sugar just gets surrounded by the water, but doesn't actually break into particles. So anything from your common ion table, ionic compounds, when they dissolve in water, if they do, they are electrolytes and they will conduct electricity. So if you're doing like an ultra endurance athletic event and you keep getting water and keep getting sugars to get your nutrition, but you don't get electrolytes, you need those two because you sweat those out, and it's an important part about maintaining your function and electrical balance in your cells. All right, so that was question 1. And I think we found out that salt water conducts electricity because it breaks into ions. Okay, where sugar water doesn't break into ions, but when salt water dissolves, it breaks up into Na plus and Cl minus. Okay, this is something I think I did a while back. We'll see if I can position this so you can see it okay. And I have a barrette right here. And I have some water going to be streaming out of this barrette. Okay, it's kind of a long tube. You can get it farther, but I don't know how well you're going to be able to see this. So anyway, what I'm going to do is run water through here. And I am going to drain this. And I don't know if you can see a stream of water or not. It's pretty small. But then what I'm going to do is take this balloon and I'm going to rub my head on my hair, and the water deflects toward the balloon. So it'll be interesting to see if you're going to be able to pick that up or not. But the water is going to deflect toward the balloon. I'll try to get that a little bit closer. without dropping my computer into the sink. Okay, rub this on my head, and water deflects toward the balloon. So water is polar. It ends up having electron pairs up here. We worked on that before, so it's more negative by the oxygen, more positive here. So water, even though it doesn't break into ions, it has a positive and negative end. Now the balloon gets static electricity, which is negative. So when the water comes out, it actually lines up so the positive is going toward the balloon, and that's why it connects and moves toward that. So the positive part of water lines up to the negative charge right there. Now it's kind of interesting, if I put a positive charge there, the water would just realign, and then the negative part would be attracted to the positive charge if I put that there. So looking back at question number 2, why does a stream of water deflect toward electrostatically charged balloon? Water is polar. It tends to have a more positive and more negative end. And polar substances tend to dissolve other polar substances as well, because the positives and negatives interact with each other. And that's why water actually dissolves a lot of ions, because the water can surround and interact with positive and negative charges. Okay, let's go to question 3. How does an increase in temperature generally affect the solubility of a solid in liquid? Okay, let's see. That is generally, if temperature is up, the solubility of a solid in liquid increases. So if I put sugar in hot tea instead of cold tea, it's going to dissolve more readily. If you do baking stuff with sugar, if you get some hot water, it gets out, you can get like the pan of brownies or whatever out pretty clean, pretty quick. With cold water, it's a lot more difficult. It's not always true, but that is true for most substances. I like to think of it as maybe the water molecules and the solute particles are moving at a faster speed and can interact and dissolve in each other, although that's not an exact description of what's going on. Okay, another question is, how does an increase in temperature generally affect the solubility of a gas in a liquid? It is the opposite, okay? If temperature goes up, solubility goes down. So let's say I open up a can of pop, and I'm saying, okay, I don't want it to go flat. I'd probably put it in a cold refrigerator instead of leaving it out on the countertop. So if you speed up the molecules, which raising the temperature does, the gas is more likely to escape that liquid. So if you keep it cooler, it's more able to hold that gas. You know, where are you going to see more freshwater fish like trout? You might see those in a cold mountain stream. You might get carp, okay, for example, which can tolerate less oxygen levels in the Minnesota or Mississippi River in the back sloughs, where there's less dissolved oxygen in the water. So if temperature is up, solubility is down for gas in a liquid, because at higher temperatures, molecules move faster and they're more likely to escape the gas molecules. Okay, question 5 says, how does the increase in pressure affect the solubility of a solid and liquid? Because solids and liquids the particles are so close together, there's really not much of an effect either way. Okay, but number 6, it says, how does an increase in pressure affect the solubility of a gas in a liquid? Give an example. So I'm going to open up a can of pop, and when I open this up, okay, it starts bubbling. Okay, because what did I do? I lowered the pressure, and then some of the bubbles escaped, so I must have lowered the solubility. So lowering the pressure lowers the solubility, some of it escapes. Increasing the pressure forces the gas molecules to stay there, and that would increase the pressure. So that's a direct relationship. The pressure is up, solubility of a gas in a liquid is up. The pressure is down, solubility of gas in a liquid is down. Okay, let's say I take some of this pop, I'm going to find a beaker here, and let's say I decide to add, and take this and pour this in here. Okay, kind of fizzy. Put a little more in. Not more on, okay, more in. All right, and what I'm going to do is add some salt to this. All right, so I'm going to take this and put some sodium chloride in here. spoonful. Let's watch what happens. Okay, it's really fizzing up. Okay, so as I add the sodium chloride, what's happening, some of the sodium chloride is dissolving. And what that means is the gas, which is held less strongly, ends up getting kicked out. So there's a competing solubility. Some of the sodium chloride dissolves at the expense of the gas, which is held more loosely. It'll get kicked out. It's like, what is that gas? It's carbon dioxide. The solute saying carbon dioxide, or the pop, carbon dioxide, I still love you, but I like sodium chloride better. Kind of salty, eh? All right, so that is what happens to pop when salt is added and why. The last question, can a solute be both dilute and saturated? So we can go back to the terms. Dilute is really not the opposite of saturated. Dilute and concentrated are opposites. Okay, so if you add more solute, it becomes more concentrated. If you add more solvent, which would be like the water, it becomes more dilute. Okay, saturated and unsaturated are based on like the size of if your tank is full or not. If it's saturated, it's holding as much as it can hold, whereas unsaturated, it's below holding that amount. Just like your gas tank in your car, okay, if it's filled up, it's saturated. If it's empty, it's unsaturated, or even if it's half full, it's still not completely saturated at that point. So what I'm going to do is maybe just show an example of something. I have some water here, and I'm going to put a little bit, just a little speck of calcium carbonate, which is chalk, in here. Okay, so you can see that just a little bit I'm going to throw in there. Okay, and then I'm going to try to dissolve that in there. And I'm going to stir this around. What's probably going to happen is it's starting to get cloudy. It's like a suspension. It's kind of like if you took water from the Minnesota River and put it in a glass, and it's kind of suspended there, but if you let it sit, it's going to sink to the bottom. So what's going to happen, it's not all dissolving. Even though it was a dilute amount, okay, it wasn't a very big amount. Okay, it doesn't seem like it's a very concentrated solution or to have a low molarity. There's still stuff on the bottom, and what's happening is, okay, it's still saturated. If you added more, it would just sink to the bottom. Why can something be dilute and saturated at the same time? It's something with a very low solubility. So calcium carbonate in water has a very low solubility. So even though I have a low absolute amount of solute in there, it's still not dissolving because its solubility is really, really low at this temperature. All right, those are questions 1 through 8. Hopefully the visuals help. Do look at the homework packet key on page, and you will see kind of the skeleton notes for that. Thanks for watching.